We're going to continue on here, chapter 14 still. So last time we were talking about obviously about weak acids and weak bases. And obviously because they are weak, they're basically like weak electrolytes and they will set up an equilibrium, which means we really do need to use an ice table here to solve. And again, we will go through sort of our normal ice table and solve for X. And in the case of the weak acid, X will equal the H plus concentration, which is ultimately what we're usually interested in, so that we can obviously get to the pH at that point. We obviously can solve these ice tables like any other ice table, so we can make an assumption if it works. We saw somewhere that did not work. So again, just a reminder, you do want to make sure you do check your assumption. When you do that, again, to check your assumption, you need to take your X value you got and really divide it by the initial concentration of whatever you're going to subtract it from, basically, and times it by 100%. And again, 5% or less is kind of the rule we're going to go with. And it would be a good one. If not, then you do need to go back, obviously, and solve it some other way. Weak bases work the same way. If it is a weak base, the difference, though, is when you do solve for X, X will equal the hydroxide concentration, and again, not the H plus concentration. So usually in that case, the route that you would take is obviously you would get to the POH, and then you got to get to the kind of pH after that. So um, it's a common problem that people have is writing the formulas again for these reactions. So you want to make sure you know how to do that correctly so that when you write the equation for a base, you end up with hydroxide and not like H3O plus or H plus or anything like that. I think that's sort of where we left off. Any questions on it out there? All right. So we talked about obviously a weak acid which has a Ka value. And when we talk about Ka values and Kb values, they are for weak acids and weak bases. And remember that sort of the larger the Ka or Kb value, the stronger the weak acid or weak base will be. Um, and we also saw one obviously here for a base, and this is our reaction here. So sometimes you have to make sure that you kind of use the correct K value. And what I mean by that is there will be some problems coming up where they will typically give you the wrong K value. So they'll give you like the Ka value when you really need to use the Kb value, or vice versa, the Kb value when you need to use the Ka value. So how do you know, again, which one you should use? Again, really, if you write the reactions correctly, which you should be able to do, the equation itself should really help you decide, what type of K value you should be using. So if you look on the product side and you see H plus or H3O plus, that's basically an acid situation. If you're using a K value, you should definitely be using a Ka value. If you look on the product side and you see hydroxide, that's just signal to you some type of basic condition, and you should be using a Kb. So again, why the importance of being able to write these reactions correctly is really important because it can help you with the calculation part. But definitely that's a really good way to kind of know, should I be using Ka or Kb is really what you see on the product side of the reaction. Now, if we take our Ka and we add it to our Kb, we could add these equations together and the A minuses will cancel out. The HAs will actually cancel out, and we're actually left with water. And water there, H plus and OH minus, and we have a K value that goes with obviously water as well. And remember that when we add K values together, we multiply these two things. And that is going to give us a really important relationship, which is if you take the Ka times the Kb, it will equal Kw. And that Kw is the same one we used earlier on in the chapter, which is our 1 times 10 to the minus 14. So this is a very quick way that if you do have the Ka value, but you really need the Kb value or vice versa, you can use Kw basically to swap it out for the one that you need. It's really the same calculation regardless of whichever one you have. You're basically just going to take Kw, which is the 1 times 10 to the minus 14, and divide it by the K value that you don't need. This does come up a lot along the way in certain calculations. And again, so you don't want to just kind of roll on autopilot sometimes when you're doing a problem. You want to make sure you look at the equation, see what's going on, that you use the right sort of expression. Questions on that there. So let's talk a little bit about acid strength. And acid strength is actually based on sort of its structure. And there's really kind of two types of acids that we come across: acids that really do not have oxygen and acids that do have oxygen. And when we look at an acid that does not have oxygen, we're really looking here, obviously, at the bond here between hydrogen and whatever it may be. So this could be something like as in the table there, HCl, HF, whatever it may be. And this bond right here is the one that will release, thank you, the hydrogen into the solution, right? Which basically makes it an acid in this case. So you may think to yourself, well, maybe it's based on electronegativity and whether or not one of these elements are more electronegative than the other in terms of the X part of it, or the negative anion. And actually, it turns out that when we look at sort of the strength of acids that do not contain oxygen, is actually bond enthalpy. That is the overwhelming thing that you look at. Bond enthalpy, as you might remember when you talked about bonding, probably you did a bunch of maybe energy calculations by how many bonds you broke, how many ones you made, right, and put them together. Um, so when we look at bond energy here in terms of group 7, basically, which is our fluorine, our chlorine, and our bromine or iodine, remember electronegativity does increase as you go up, but in this case, it's actually the bond energy that's our enthalpy that's really important here. And the stronger the bond enthalpy, the weaker the acid is going to be. And it's just as simple as I need that H to come off here to be an acid. So if it takes a lot of energy to break that bond, not a lot of H is going to come off in comparison to somebody that doesn't take a lot of energy to break that bond. So what we can see here is HI actually only takes 298 kilojoules of energy versus 568 there for HF. And that means that HF is actually going to hang on to its hydrogen more than HI would. And that's why actually acid strength increases as you go this way. It's much easier to remove that hydrogen there from HI, and then HBr, and then HCl. And it takes a lot harder to remove it there from our fluorine. That's why actually out of all those, HI is strongest acid of all those groups there. People always hear about hydrochloric acid, and I think it's the strongest, but it's actually in this group, is actually HI would be the strongest because it's going to release is hydrogen a lot easier than everybody else in that group. So if you're comparing between two acids that do not contain oxygen, you really want to look at the bond enthalpy to do that comparison. And again, the stronger it is also related really to size as well, right? So like as we go up, size gets smaller, right? So since it's smaller, it's going to be stuck on there a lot tighter and closer to the hydrogen, and it's going to be harder to kind of break. And again, here's sort of a on the periodic table, some of our acid type of solutions, increasing bank strength as we kind of go away from the left of the periodic table, down and away, and increasing acid strength as we go down into the right here. So that's what we see. Now, when we do have oxygen involved, pretty much this is sometimes referred to as oxyacids because they have oxygen involved. And for the most part, most oxyacids will have pretty much this bond here, which is the OH bond. And the OH bond is a polar bond based on difference in electronegativity values, right? Hydrogen more positive, oxygen more electronegative. So it's going to kind of suck the electrons towards itself, making it more partially negative in that case. So when we do have oxygen involved, we do look at really one of two things depending on the situation. We will sometimes look at the electronegativity of the central atom, or we may look at the oxidation number. And those are the two things that we look at. And depending on the situation, we may look at one versus the other. And we'll talk about why we may do that here right now. So let's take a look at the first order situation. Now, if we have an oxyacid where the central atom are from the same group and have the same oxidation numbers. So when we assign oxidation numbers, which you might remember how to do, but if not, oxygen is a really good place to start. Oxygen is -2, -2, -2. Hydrogen is +1. So if we add all that up there, that's -2, -2, -2 is -6. +1 is -5. This whole thing is neutral, which means the chlorine here is carrying a +5 oxidation state. If we do the same thing over here to this acid here, -2, -2, -2, +1, same deal, 2, 4, 6, and +1 is -5. And the bromine here would be carrying a +5 oxidation state. A reminder that the oxidation state is not the charge necessarily that you associate in an ionic compound. It is the charge that that atom has when it is bound in a covalent compound and sharing electrons maybe equally, unequally, and it can gain, things that we normally think about as being negative can have a positive sort of charge. Because in this case, basically those oxygens are sucking the electrons out and making the bromine more and more positive. Now, in this case, we cannot compare the central atom here as they both have the exact same oxidation number. So in this case, what we would be looking at is electronegativity. And the greater electronegativity, the stronger the acid. So the idea here is this, right? Since, again, they both basically share the same oxidation state, we have already a polar bond where those electrons are basically moving in on that OH bond. And now with a greater electronegativity here in our chlorine versus our bromine, it's going to kind of pull those electrons in a little bit more, right? Because it wants to basically pick them up. And what that's going to do is weaken and weaken this bond and make this H a lot easier basically to pop off. Less greater ease on the left there than we do on the bromine, which is also going to kind of bring the electrons in, but not as much as chlorine, again, because chlorine is more electronegative. So in this case, where we have a central atom that's the same oxidation number, we want to look at electronegativity. The greater electronegativity, the stronger acid. So here, our chloric acid there would be stronger this case. Our HClO3 would be stronger than our HBrO3 in this case. Any questions on that one there? Now, what is sort of the opposite situation? Opposite situation is we actually have the same sort of element, which means they would have obviously the same electronegativity value. So we cannot use electronegativity as our source of comparison. So in this case, because they're basically the central atom in all these cases is the chlorine, we basically cannot use obviously electronegativity. So we also go by oxidation number. And again, if we just kind of go around here, this would be -2, -2, -2, and -2. A little +1 action there. That's a -8 and +1 is a -7. Once again, this is a neutral acid, like most of them. And that means that the chlorine in the middle here is carrying a +7 charge. Here we have the one we just did, -2, -2, -2, +1, giving us, again, a -5, so +5. Over here, -2, -2, +1. So that's a -4 and 1 is -3, so the chlorine here is +3. And lastly here, -2 and +1, +1 happening here for this chlorine. So in this case, it's really sort of the same idea. The chlorine in this case has a much larger sort of positive charge, if you will. And again, with that sort of polar bond where the electrons are heading this way, it may be attracted obviously a lot more to that chlorine in the center because it does have a greater positive charge. And that's again going to weaken this bond more than it is over here. Remember, opposites attraction and the strength of that charge or that attraction is based on the size of the charge. So the larger the charge, the greater the attraction happens. So in this case, this guy down here, perchloric, would be our strongest, our next strongest, our next strongest, and the weakest out of all these would be the last one here. Questions on that there? So if you have an oxyacid, kind of same central atom, you're going to be looking at oxidation numbers. If you have an oxyacid where they have the same oxidation state in the center, you're going to look at electronegativity. Good question. All right, so the next thing we're going to talk about is actually salts, and let's back up a little bit maybe before we get there. So remember that when we have a reaction basically between an acid and a base, we basically make two things. We make a salt and water in most cases, right? And obviously we have our water, we have our salt, and our salt is really just an ionic compound. So our salt is an ionic compound. It is essentially, if you want to think about it in a lot of cases, especially with the strong acid, strong base situation, or in a lot of acid base situations, the H plus is provided by the acid, the OH minus is provided by the base, and that's where water comes from. Our salt is usually the ions that are left over. For the most part, they're like the spectator ions that are kind of left over in that case. So what's the deal with a salt? Well, in certain cases, what can happen is when you have a salt that's present that really came from an acid and a base, this salt in some cases has the ability to react with water. So it has sort of the ability to continue to react with water, which isn't a problem because water's hanging out with it basically in this situation, right? So there's plenty of water in there, and this salt can react with it. Now, in some cases, this salt will react with water in a way that it will basically take the H plus from the water. And the result of that is, in terms of the solution, is when water loses that H plus, it then creates some hydroxide. And because it creates some free hydroxide as a result of this reaction, we will expect some basic situation to sort of occurring, right? Because we're going to be increasing the amount of OH minus that's in that solution. Now, in other cases, the salt itself can react with water and basically send the H plus over to water. And the result of that is we will then generate some H3O plus, which is going to make that solution more acidic. And there are also some salts that actually won't react with water as well, so they won't really do too much in that case. This type of reaction here is what is sometimes referred to as a hydrolysis reaction, and basically just means you're reacting with water in this case. So as sort of a byproduct of a reaction of an acid and a base, you will create these salts, and these salts, based on where they come from, will have the ability to, again, sort of react with water and either produce hydroxide, which will make the solution more basic, or it will react with H3O plus, or react with water to make H3O plus, which will make the solution more acidic. Now, one of the really important sort of relationships that is important to remember here when we're talking about salts is something that we talked about earlier on in this chapter, and that was the relationship between an acid and its conjugate base, or a base and its conjugate acid. So if you remember earlier on, if we have an acid right on one side of sort of the arrow, if you will, on the other side we have a conjugate base, and that Bronsted-Lowry sort of definition. If we have a strong acid, its conjugate base will be relatively weak. And what that means in the sense of salts and hydrolysis reactions is it will not go through hydrolysis. Now, if you have a weak acid, its conjugate base is going to be relatively strong. And earlier we talked about the idea that it's going to be strong, but it's not as strong as a strong base, but it's strong in the sense that it will go through hydrolysis. And the same sort of relationship for our base and our conjugate acid. And if our base is strong, is conjugate acid will be relatively weak, which again, just like above, means it will not go through hydrolysis. So it will not react with water and produce any H plus or OH minus. And if you have a weak base, its conjugate acid is going to be relatively strong, which means it will go through hydrolysis. So that relationship of sort of opposites there is really important when you're dealing with salts. It is also sometimes really helpful when you're dealing with salts to sort of think about kind of where it comes from. And if you think about where it comes from, it could help you understand how it will react with water if it does react with water. So it's really important to kind of think about that relationship. Any questions on that? Yeah. Mhm. Correct. So the only way you could really make a salt is usually from a reaction of a acid and base, so sort of a product of that reaction, and that salt is technically is conjugate acid or base, so those guys along the way. And sometimes we do pick it up, by the way, just from the salt part. We don't kind of, in a lot of problems, they don't talk about, where it came from. So that's why, again, it's important when you look at a salt to be able to maybe figure out, what's the two parts come from, right? The two parts of the salt will always come from basically an acid and a base, right? So you're going to have basically two parts to your salt, a positive ion, right, and a negative ion. So those guys come from an acid and base. You want to kind of think about, what acid and base they probably came from, which in a lot of cases is not super hard to sort of figure out. A lot of times it's fairly obvious, and you could then identify as, was that a strong acid or a strong base, or was it a weak acid or a weak base? All right, so we have that relationship. Let's talk about first, though, salts that are neutral. And as I mentioned before, there are certain salts that are neutral, and these salts are really the ones that we just made on our list that do not go through hydrolysis. So these are basically salts that originated from basically a strong acid or a strong base. So that is a salt like sodium chloride, right? So if we think about sodium chloride here, sodium chloride is a salt, which means when it's in solution, it will break apart into really these two ions, sodium ion and a chloride ion. Is basically what's going to be floating around in that solution. Now, if we think about this salt, you could probably imagine maybe the reaction of an acid and base that would produce that. What acid and base might produce this salt? Acid like what acid has Cl in it? Yeah, HCl seems good. Yeah. And a strong base that has sodium in it, like sodium hydroxide, right? So this reaction of hydrochloric acid and sodium hydroxide is most likely, right, our double displacement reaction happening here, right? These two guys go this way, this way. This is what's going to produce our water and our salt, which is sodium chloride in this case. Our salts, obviously our water. So when we think about where this salt came from, HCl is definitely a strong acid, right? We have that list of some strong acids that we talked about. And again, that kind of big list of hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydriodic acid, and sulfuric acid, right? These are our list of our strong acids. And remember that most of our strong bases come from group 1 and 2 on the periodic table that has hydroxide in it, right? So again, if you go kind of like lithiums down to sodium and go right over there to calcium. I'm sorry, not calcium, but to potassium, and then hang it right to calcium and then down that way. That's where a lot of our strong bases come from. So in this case, because it comes from a strong acid really and a strong base, this salt will not go through hydrolysis and is considered a neutral salt, which means the pH here would be a pH of 7, which is neutral in this case. So this salt's really not going to affect really the pH of the solution, as it will not continue to react with water in this case. Any questions on that there? Now, let's talk about a salt that maybe will do something. And basically, though, a neutral salt is also defined as anything from group 1 or 2 on the periodic table. And that's, again, really where your strong bases come from. If you have any of those guys, except for beryllium, will be considered basically a neutral salt and will not go through hydrolysis. Now, there are some salts, like, for example, if we take something, I go do it on this page, I think. We take something like sodium acetate, right? And if we take something like sodium acetate, that is a salt that will break apart in solution into sodium ions and acetate ions. Right? And by the way, since a salt's an ionic compound, it's also a strong electrolyte, which means it's not going to stay together in solution. It's just going to completely break apart, basically, in this case. So when you're looking at a salt, you really want to look at basically both parts of the salt, and you want to determine, will there be anything there that will go through like hydrolysis? We may also want to think about maybe where these came from. So what acid could perhaps this come from? Acetate most likely came from acetic acid, right? So again, as I mentioned before, not super hard in a lot of cases to sort of think about where maybe these salts came from. That's acetic acid. And sodium, group 1, so probably a strong base like sodium hydroxide. And again, this is going to do its double displacement reaction here. And they're going to switch partners like so, and that's going to produce our water and our salt here that we see above. So now when we take a look at our salt, we can analyze really where it came from. So a strong base here. Acetic acid is what type of acid? Strong or weak? It is weak, and if you're not sure, I know it's weak because it's not one of the 6 that was on my list a second ago, right? That's strong, so that's a good way to know that. So this is a weak acid. So now we kind of have an idea of where all of our things come from really here, right? The acetate comes from our acetic acid, and really our sodium comes from our sodium hydroxide. So now when we're analyzing, is there anything here that's going to do any type of hydrolysis reaction? We know right off the bat that is from group 1, which means, as we can see here, it really comes from a strong base, which means, as we just saw, that is going to be considered a neutral salt, right? So we don't even have to worry about it reacting because that's going to be neutral. But what about the acetate? It comes from acetic acid, which is weak. And because acetic acid is weak, that means acetate in this situation is going to be relatively a strong conjugate base, right? And that means it will go through hydrolysis here. So this part of the salt will go through hydrolysis. And that means always we take the part of the salt that's going to go through hydrolysis. And the good news is, in a hydrolysis reaction, the other guy is always water, right? So that is basically what hydrolysis means. It's going to react with water. Now, let's just say you got to this part, and you're not really sure maybe what's going to go on or how it's going to react. Understanding where it comes from could also help you understand how it's going to react. So we just saw that it came from a weak acid, which means, as I wrote here, this is going to be a conjugate base. So what I now know is when my acetate reacts with water down here, it's going to react as a base, and that is a Bronsted-Lowry base, which means it should donate or accept the H plus. A base will accept the H plus, right? So it's going to pick up the H plus in this case. And when it does, The good news is, or maybe it's good news or bad news, it will always make where it came from. So this thing came from acetic acid, so it will always make where it came from by picking up that hydrogen. And when the water loses the H plus, it will then produce hydroxide in this case. First off, any questions on that? If I had to venture a guess in this case, this solution should be acidic, basic, or neutral. Solution should be, what do you think? What do you see on the product side? See a lot of hydroxide, right? And free hydroxide means pH goes up, right? Because the H plus goes down, right? And this thing should be basic, yeah? So just by writing the equation correctly, we should know that the pH of this salt solution should actually be basic because we are generating a free amount of H plus. By the way, that is like a equilibrium type reaction, which means if I wanted to calculate the pH, I would need to do a ice table, yeah? And also quite important here is what type of K value should I use? Ka, Kb? Yeah, I would need a Kb value here because we have hydroxide. And I will tell you, probably in this question, you would be given the Ka value for acetic acid, which is this is a situation I was talking about earlier, where you would probably need to also use that Ka times Kb equals Kw to swap it out to the K value that you need. So salt problems, hydrolysis problems historically very commonly will give you sort of the wrong K value in a sense in terms of what you need to use to calculate it. So these are definitely the problems where you definitely have to kind of swap out the K for the right one you need. Again, why writing this reaction is really important because if you wrote H3O plus, you're going to roll with the Ka value and you get the wrong answer in this case, right? So you want to make sure you do that. By the way, the other thing you also want to make sure of is when I solve for X, by the way, in this case, it equals the hydroxide concentration, right? So you got to go POH first, right? And then the pH. So these are things you want to kind of think about as you go through it. Any questions for that? So if you have a salt that basically came from a combination of a weak acid and a strong base, you will end up with a salt that will go through hydrolysis. It basically will always pluck off the H plus from the water. It will always produce hydroxide, and you'll always end up in a basic situation in that deal. Any questions on that there? All right, so that's what we just talked about there. And again, as you can see, you got your hydroxide. There is also acidic salts, and for example, we'll take a look at this one here. Let's say we had ammonium chloride as our salt. Ammonium chloride here is a salt that will break apart into NH4 plus and Cl minus. So once again, if we're just sort of thinking about how we maybe got to this salt, we could think about it maybe a step before. And in this particular case, NH4 plus looks very much like NH3, which is ammonia. And ammonia reacting with hydrochloric acid, for example, would do that. That would get you the H plus heading that way, and that would produce your NH4 plus and your Cl minus, which is basically the salt that is produced in this case. And in this case, this is our acid, which is a strong acid. And this is actually a weak base that we talked about. So this is essentially where our salt comes from. So once again, when we look at the salt, we want to think about, is there anything there that will go through hydrolysis? So if we start with our NH4 plus, I know that it comes from here, NH3, which is a weak acid. I'm sorry, weak base. And that automatically means that's a weak base. So this guy's going to be a relatively strong conjugate acid, right? And that also means that it will go through hydrolysis in this case. In terms of the chloride obviously comes from our HCl, which is a strong acid. Again, that falls under what we first talked about. That is going to be a neutral salt. You're not going to get hydrolysis happening with that guy because it's going to be a relatively weak conjugate base in this case. So out of those two parts, basically it's going to be our NH4 plus that's going to react with water. And once again, if you're not sure how it's going to react, we want to think about where it came from. So it came from a weak base. It's going to be our conjugate acid. And that means that when it reacts with water, it will react with water as an acid. Again, the Bronsted-Lowry definition of an acid is something that will donate an H plus. So he's going to send the H plus over to water. The result of that is, again, as I said a second ago, you will get where it came from. So when it donates that H plus over, you are left with really where that NH4 plus came from, which is ammonia. And when that water gains the H plus, it will make H3O plus, right? And now in this reaction here, we see the presence of H3O plus, which should automatically tell us the pH of the solution should be acidic, right? And again, it is a weak sort of equilibrium that's set up here, which means we will need to do an ice table. And we also would need a Ka value in this case again, and because we are producing H3O plus. So again, as I mentioned, writing those equations can definitely help you with the calculation part to make sure you're kind of doing it correctly. In this case, when we do solve for X, it actually does equal the H3O plus, which means you can then go directly into your pH. So this is an acidic salt, which typically arises from a reaction of a weak base with a strong acid. And when you got that combination, you will always have a salt where the part that came from the weak base will react with water and produce H3O plus and make the solution acidic. Questions on that one there. Now, in addition to kind of a traditional salt that is acidic, there is also another way that we can make an acidic salt, and that is from metals that are sort of complex ions that are hydrated with water or other things. So we have an aluminum in this case that has 6 waters. Maybe I'll do it here. I'll go this way. Back this way. So we have an aluminum here with 6 waters and a +3 charge. And another way we can kind of get an acidic salt is a metal. A lot of times it's a transition metal with a fairly high positive charge, 2 or 3. Aluminum occasionally, maybe beryllium as well, but most of the time it's going to be something like this. What is this? This is basically this situation. It is basically an aluminum that has 6 waters surrounding it. And I won't draw out all of the waters. I'll just write them as H2O. By the way, they are attached to the oxygen. 1, 2, 3, 4, 5, and I'll just draw out one of them here, like so. So we basically have this guy. This is what a complex ion is, basically. By the way, it's also kind of like when you write this, aqueous is basically that. That's what that is. In this particular case, what we have going on is an overall charge here, a +3. And that +3 charge is coming from the aluminum, which is positively 3 charged. Each of the waters are neutral in this case, right? Obviously. So what happens in this situation is when you have this type of arrangement, another water by itself, the regular old water rolling through, can actually pluck off the hydrogen. And when it does so, it's going to send it back that way. And what you're going to end up with as a result of that is we are going to produce, in this case, the hydronium ion, which is H3O plus, basically, in this case. And that is what's going to make the solution acidic. What does that leave this guy? Well, this guy gets left with basically the aluminum and really all 5 of those waters basically were not touched, and you end up with an OH here, right? Which is like OH minus, right? Overall charge changes by 1 because minus 1, right? And plus 3 gives you that. So this guy, when we look at that formula, this guy ends up with, again, all 5 of those still intact in an OH, which is OH minus. Again, plus 3 minus 1 leaves an overall plus 2. Scary looking thing that you will know how to name by the end of the semester. And we will make H3O plus in this case here. So metals that are sort of hydrated like that, they have what are referred to as ligands attached. Um, can also do that again by basically donating an H plus there to water that's floating around, and it will produce that H3O plus. Questions on that? And again, that's basically what this formula looks like. All 5 of them intact. We took out an H from one of them. All right, so why don't we try one here? What is the pH of a 0.45 molar potassium chloride solution? Okay, let's take a look. So in this particular case, we have potassium chloride, which obviously is a salt, so it's going to break apart into K plus and Cl minus. So again, we want to kind of analyze our salt and see if anything is going to go through hydrolysis. How about the K plus? Will that go through hydrolysis? That will not because it's group 1, which basically means it most likely came from KOH, which is a strong base. And that means that it's not going to go through hydrolysis. How about the chloride? Will that go through hydrolysis? It will not either because it most likely came from HCl, which is a strong acid, which means in this case, both of these parts of the salt is not going to go through hydrolysis, which means it's a neutral salt. No calculation actually needed, just a pH of 7, right? In this particular case. Questions on that there. All right, let's take a look at one where maybe there's a calculation involved. Let's try this one here. Consider a zero point 0.3 molar solution of NaF. The Ka value for HF is 7.2 times 10 to the minus 4. What is the pH? This one you might need a calculation. Okay, let's take a look. So we have a salt here of sodium fluoride. So obviously that is a salt that's going to break apart in solution and produce really sodium ion and fluoride ion. And really at this point, what we got to decide is, will any of these go through basically hydrolysis, right? So obviously, right off the bat here, we could probably rule out our sodium as again, it most likely came from sodium hydroxide. It is group 1 on the periodic table. So again, that's going to be neutral, so we don't have to worry about it. Now the F minus here most likely came from, I would say this guy right here in the problem. HF seems like a good source of it. And that obviously is an acid since there's a Ka value. And by the way, since there's a Ka value, I also know what type of acid that is a weak acid, right? So again, don't overlook a lot of the helpful information that's sometimes in these problems. So I see a Ka value for HF, which is not F minus. Obviously, they're related to each other, and that's a weak acid, which means this is going to be a relatively strong conjugate base. And that also is going to check the box of it will go through hydrolysis here. So it is going to be the F minus that's going to go through the hydrolysis. So our reaction here is going to be F minus plus our water. And because it is a conjugate base, it will act as a base here when it reacts. So it's going to accept the H plus. Also, just common sense tells us it doesn't have an H to give, so it can't really give something it doesn't have. So it's got to accept the H plus in this case. And the result of that is, again, we will always produce where it came from, which was nicely supplied to us in the problem here. It will always produce that HF. And in this case, we will produce hydroxide, right? First off, any questions on the reaction? So a lot of times these problems have a lot of helpful information in it that sometimes people just kind of overlook. So don't overlook it. By the way, before I even finish my calculation, I should end up with what type of pH? Acidic, basic, or neutral? I should definitely end up with basic, which is a good way to check yourself at the end and make sure that you did it right. Again, because we do have hydroxide. At this point, we're already just going to do an ice table. And again, we do have the concentration of this guy, which is 0.3 molar. It is a 1-to-1 relationship between that and the F minus, which means the concentration F minus will also be 0.3 molar. So we'll go 0.3. We're going to 0 and 0. Change will be minus x plus x plus x. We're going to 0.3 minus x, x, and x. Questions on the ice table here. This is going to go into my K value here, which is my products divided by my reactants. And that is going to be a K, A, B, C, D, E, F, G. This should be a K, B. Also know it should be a KB because I have hydroxide here, right? I am not given the KB here, right? I am given the Ka4HF. So as we talked about earlier, this is where our Kw equals Ka times Kb comes into play. We could use that to calculate our Kb value. So our Kb value in this case would be Kw divided by Ka. That is 1 times 10 to the minus 14 divided by 7.2 to the minus 4. Going to give us a KB value in this case. Oh, looks like I'll call it 1.4 to the minus 11. So again, that is definitely the K value that we want to use here. A lot of people just roll with the K value that's given to you. So again, you got to kind of think about what's going on and not just roll through it. That's going to give us x squared over 0.3 minus x. That seems like a small K value, so why not assume x is equal to 0? And if I do that, I will end up with, not that, I will end up with x squared divided by 0.3 equals 1.4 times 10 to the minus 11. Again, I'm going to multiply and then square root it. And that will get me here 0.3, little square root action. That's a lot of zeros. I'll do a little scientific notation. It's going to give me an x value of 2.04 times 10 to the minus 6. Again, we do need to check it, so we'll divide that by 0.3 and times it by 100%. And in this case, I don't even think you're at 0.1%, so the check is good in this case, yeah. Yeah, so I think you're way, way under even 0.1. All right. Because that x value is good, that is what our hydroxide concentration will equal from our table. So remember that is the hydroxide and not the H plus. So we do have to POH it first here. So our POH is going to be minus the log of our X value there, 2.04 minus 6. So minus the log 2.04 to the minus 6. Looks like maybe a 5.69. Now, if for some reason you thought this was the pH, you hopefully at least know that you should be basic, and that should not sound good to you because that definitely would not be a basic pH. And it's not because it's actually our POH. So we do have to subtract 14 from it. So our pH here would be 14 minus 5.69. That's going to get us an 8.31, which does sound basic to me and does make sense in this case. So again, there's a lot of places where if you just kind of roll through it without maybe think about what's going on, there's a lot of places you can get in trouble on these type of problems. So again, you got to really kind of think about what is happening so that you do the math correctly. Any questions on any part of that there? All right, let's try maybe another one here. Or not. Let's see. We'll change the page maybe. All right, so give that a go. What is the pH of a 0.75 molar solution of soda? Take a look. We got, again, another salt here, ionic compound, a good way to recognize it. So we just want to analyze our salt and see if we got anything doing some hydrolysis. So this will break apart into sodium and a little cyanide here. Once again, in terms of our analysis here, we have our sodium, which is group 1, which means it's a neutral salt, not going to go through hydrolysis. Once again, here we have CN minus, which again, I don't have to go too far to figure out where it came from. It came from HCN, which has a Ka value, which tells me again this is a weak acid, which means it's going to be a relatively strong conjugate base, and it is going to go through hydrolysis. So again, that's going to be our hydrolysis reaction. We're going to take CN minus, react it with water. And again, because it comes from a acid, it's going to act as a base with water. And again, in this case, it's going to accept the H plus, as again, it doesn't have an H to give, right? So it's got to only accept in the situation. That again is going to give us where it came from, which is HCN. And when our water gives away that H plus, it becomes hydroxide. So much like the previous one here, we should expect this guy to be basic, right? Because we are producing hydroxide. And in our calculation, we also need the Kb, right? Because again, we are producing hydroxide in this case. So we'll do our ice table here first. That's going to be our 0.75. Our 0 and 0, once again, it is a 1-to-1 relationship between that. So the concentration of that guy is the same. Change here, minus x plus x plus x means at equilibrium 0.75 minus x, x, and x. Any questions on the table there? This is going to go into our Kb expression that we need. And we do also have to calculate our Kb. So our Kb would be our Kw divided by Ka. So 1 times 10 to the minus 14 divided by 6.2 to the minus 10. And that's going to give us a Kb value here of looks like 1.6 times 10 to the minus 5. So putting that in here, 1.6 times 10 to the minus 5, putting in our x squared over 0.75 minus x. We will assume x is equal to 0. Makes it a little bit easier to do, obviously. And in this case, that's going to give you x squared over 0.75 equals our 1.6 times 10 to the minus 5 in this case. Again, we're going to multiply and then divide, not divide, but square root. So we'll take our Kb times it by 0.75 and square root it. That is going to give us an x value of 3. We'll call it 5 times 10 to the minus 3. We do want to check it, so we'll divide this by 0.75 times it by 100%. Just to make sure everything's good. I would say probably in most cases you're going to be okay on this still. The check is good. Once again, looking back at our table, we can see our X value does equal higher hydroxide concentration. So the hydroxide concentration is the same number. That allows us to go into our POH, negative log of 3.5 times 10 to the minus 3. And that's going to get us there. Looks like 2.46. And again, our pH would be found by taking 14 minus our 2.46. Looks like 1154. which is definitely a basic pH in this case. Questions on that there? So these two happen to be basic. Obviously, acidic works exactly the same way. The only difference is when you get X, you got H plus, so you go right into the pH. Obviously, you don't have to do the pOH. Questions on salts there. So again, very commonly, people just kind of overlook some of that information that's in there. It can be very helpful to work through the problem with. All right, let's take a look here. Here's a prettier picture of that aluminum that we were talking about earlier. That's an acidic salt again because it produces H3O plus. Now, the problems that we did and the problems that we talked about so far, when we look at the salt, only one part of the salt will go through hydrolysis. And it is definitely possible that you could end up with a salt where actually both parts of it will go through hydrolysis. So, for example, if I had NH4NO2, this is NH4 plus, which as we saw, definitely will go through hydrolysis as it comes from NH3. This is NO2 minus, that's nitrite, ITE. That comes from nitrous acid, which is a weak acid, yeah, which means it would also go through hydrolysis as well. So it definitely is possible if you combo two weak things together, you're going to get obviously a salt that came from two weak things that can go through hydrolysis. Obviously, the calculation is a little bit complicated on that situation. So typically what we do for that situation is we compare the Ka value to the Kb value. So if the Kb value for the anion, the negative guy, is greater than the Ka value for the cation, we would assume that this thing would be basic and you would do the Kb calculation. Yeah. If you compare the Kb for the negative guy and it's less than the Ka value for the positive one, that means the acid part is bigger. And we would assume that's going to be acidic and you would do the Ka calculation. If they are about equal to each other, then it will probably be a neutral solution. Yeah. So here's sort of a table of what we talked about with our salts. Again, anything from strong acid or base going to be equal to 7. Anything that basically comes from a weak acid will be basic. Anything that comes from a weak base will be acidic. And again, if you have both that will go through, you do have to do the comparison there. And obviously, any type of metal ion that has some water surrounded it, or not even if it's just water, but any type of large positively charged metal, like you see there, iron 3 nitrate, will go through hydrolysis. So again, here, the iron 3 part of it will go through hydrolysis. The nitrate comes from nitric acid, will not go through hydrolysis in this case. So again, it's going to be the larger charged positive metal that's going to do that. Any questions on that there? All right. I think that is probably a good place to lay it up.